Welcome to another episode of Elementary Maths with Solid Club. My name is Akin Loco. Today we'll be introducing the concept of calculus and we'll be starting from limit of a function. The concept of a limit is the foundation of calculus. It describes how a function behaves as the input variable approaches a specific value. We say that limit of a function f of x as x approaches a number a is L and is written this way. The whole idea of limits can be explained this way. If we have a function f of x, that is a function in which the variable present is x, then we can limit that function to a particular number a, for instance, and that implies that if we substitute values that are approaching a, that are getting closer and closer to a into the function, then the entire function will also approach a particular value L. Now let's see some examples that makes this clearer. Example 1.1.1, evaluate the limit of 3x squared minus 5x plus 1 as x approaches 2. First of all, the function is a polynomial function, a simple polynomial function, and the first step when evaluating limits is to plug in the limit, the a, that is the number we are setting our variable to approach, right? And in this case, a is 2, x is approaching 2, so we'll plug it in directly. We call that step direct substitution. That's the first step for solving any problem involving limits. And when we do that in this case, we have a result 3. Now what we'll check after, whenever we do direct substitution, if we have a real valued result, that is a defined answer, then that is the limit of the function. And in this case we have 3 is real valued and is defined, and so 3 is our answer here. Now the interpretation of this answer is it means that for this function 3x squared minus 5x plus 1, as we keep substituting values that are approaching 2, values like 1.9, 1.91, 1.95, 1.97, 1.99, we'll see that the results we'll be getting as we keep substituting those values to this function, the results we'll be getting will be approaching 3 as well. They'll be getting closer and closer to 3. So we can therefore place a limit that as values of x approach 2 and we'll substitute them into this function, then the entire function will also be approaching 3. But we'll never get to 3, but we'll set that boundary that 3 is the limit. That's the meaning of the solution we always obtain when we solve problems regarding limits. This second problem is a case where the function is rational. That is, we have a numerator and a denominator. The function looks like a fraction, and the steps I told you remains the same. First of all, go by direct substitution. While our variable is approaching -1, we'll substitute -1 directly into the function, and luckily we have a real valued number as result, 4/3. And so it means that as values of x approach -1, this entire function will approach 4/3. Same thing in this next example, we have limit as x tends to pi for the function sine x/2. This is a trigonometric function because of the sine function that we have here, and if you go by direct substitution, that is plugging in pi for everywhere we have x in the function. We have a real valued result as well, which is 1, and so we're saying that as x approaches pi, sine x/2 will approach 1. Now, there are cases where direct substitution will give us results that are undefined or indeterminate. Then we now have to apply other techniques to be able to resolve such functions, to get the limits of such functions. We can apply techniques like factorization, rationalization in such cases, and then there is a very popular technique called the L'Hopital rule, but we'll be introducing the L'Hopital rule after differential calculus because it applies differential calculus. Now, for a problem that involves factorization, we have this function, for instance, x squared minus 9/3. We want to limit it as x tends to 3. So move with the same procedure, direct substitution. By direct substitution, we plug in 3 into the function, and you can see the result we're having is 0/0. Any fraction with 0 at the denominator is undefined, so we don't want results after our direct substitution with denominator 0, or there's one other one we'll see that involves infinity. We don't want results like that, they are undefined. Now take note, 0/0 is not 1 and 0/0 is not 0, right? If you do direct substitution and you have a result of 0, 0 is a defined number, and that will be your result. But in this case, we're having 0/0. That 0 at the denominator is what makes the result undefined. So we need to proceed by applying the factorization technique in this case. We're doing that because we can spot a difference of 2 squares at the numerator. X is squared and 9 we know is 3 squared. And the difference of 2 squared from our basic algebra is split this way: positive and negative factors in 2 brackets. That is, for x squared minus 9, we have x minus 3 times x plus 3, and our denominator remains the same, x minus 3. So x minus 3 can cancel out x minus 3, and we'll be left with x plus 3. So you can see we've been able to represent that function by the help of factorization. Now we'll apply direct substitution again. By direct substitution to our new function, now we'll just plug in 3 for the place where we have x. Whenever we apply direct substitution, you should have noticed that the limit usually disappears, because at that point we are evaluating the limit already. So plugging in 3 here, we have 3 plus 3 and 6. 6 is a real valued number and it is defined, so that's our solution. It means that fraction x squared minus 9 over x minus 3 would approach 6 as x approaches 3. That's the explanation of our result. Now, a case where rationalization is applied is this example, where we have to evaluate root x plus 4 minus 2 all over x as x tends to 0. Of course, rationalization is applicable wherever we have surds. Now, but first we go by the usual process, direct substitution. Our a is 0, so we plug in 0, and this gives us 0 over 0, which is indeterminate or undefined, and so we have to apply a technique. In this case, rationalization can be of help. To rationalize, it simply means you multiply whatever fraction you have by the conjugate of the surd in the numerator, right? And in our numerator, the surd we're having is root x plus 4 minus 2. The conjugate will be root x plus 4 plus 2. Conjugate simply means changing the sign between two terms in the binomial, and when we do that, that is multiplying by the conjugate over the conjugate. Of course, conjugate over conjugate is just simply 1. Any number divided by itself is 1. So it's not really like we're changing anything, but we need this expansion to be able to represent our original problem so that we can apply direct substitution again and hopefully get a defined result. Now, when we do the expansion at the numerator, we have this. Of course, the numerator is now looking like a difference of 2 squares, and it results in this. You can take your time to do the expansion. Of course, it's a binomial against another binomial, so you multiply pointwise, that is root x plus 4 times root x plus 4, then plus root x plus 4 times 2, then minus root x plus 4 times 2, and then minus 2 times 2, right? So that gives us this at the end of the day. The two terms in the middle we cancel out, that is minus 2 times root x plus 4 and plus 2 times root x plus 4. Those ones to cancel out, will be left with just x plus 4 minus 4, which is x. At the denominator, we leave it the way it is because we need this x to cancel out the x we now have at the numerator. So those x's will cancel out and we'll be left with this function now, 1 over root x plus 4 plus 2. We'll apply direct substitution again, that is plugging in 0 for everywhere we have x in the name function, and finally we have 1 over 4 as our result. It implies that as x approaches 0, that function root x plus 4 minus 2 all over x approaches 1 over 4. We have another example here. This example says evaluate 1 over 2 plus h minus 1 over 2 all over h as h approaches 0. As you can see, there's a twist in the choice of variable here, so it's not every time our variable will be x. In this case, the variable is h. So we'll proceed with the usual process. First step, direct substitution. Of course, we'll have a 0 denominator, and that is undefined, and so we proceed by another technique to be able to represent the function and see whether direct substitution at that point will now give us a defined solution. To represent this function now, we can try to simplify the function further. We don't really need to apply factorization or rationalization because it's not even applicable here. And so to simplify this function further, we can see that in our numerator, this function is rational. In our numerator, there is our numerator contains two rational functions as well, subtracting each other. Inside our numerator, we have 1 over 2 plus h minus 1 over 2, right? Then all over h, that is divided by h. That's division by h is the same thing as multiplying by 1 over h. So let's just have that at the back of our mind. And so let's treat that numerator now. Treating numerator, will apply LCM. Our LCM will be 2 times 2 plus h, which is just the multiplication of both denominators there. And we'll use the LCM to multiply each of the terms, and at the end of the day we'll have minus h over 2 into 2 plus h, and then we'll multiply it by that 1 over h. We'll now have this minus h over 2h into 2 plus h. Just pause and follow my explanations with what you have on the screen. You should be able to get it. Next, we've been able to represent the original function. Then we'll try direct substitution once more. Direct substitution, we'll plug in 0 for h, and we have, okay, before we plug in 0, there's a common factor h that can cancel out at the numerator and denominator. So we'll be left with minus 1 over 2 into 2 plus h. Then we can plug in 0 now. So our limit disappears and we have minus 1 over 2 into 2 plus 0, which is minus 1 over 4. Minus 1 over 4 is defined, and it implies at the end of the day that as h approaches 0, this entire function approaches minus 1 over 4. Now, we have cases involving infinity. In this case, we always apply the rule that says we divide the numerator and denominator by the highest power of x present in the denominator, right? And then we should take note that limit of a constant over x raised to power a constant is always 0 as x tends to positive or negative infinity. We'll see the explanation of all this in this example now. In this example, we're told to evaluate this function 3x squared minus x plus 4 all over 5x squared plus 2x minus 1 as x tends to infinity. Now, in this case, we identify the first, the highest power of x in our denominator, which is x squared, appearing with 5x squared, that first term, x squared. So we'll divide both the numerator and denominator by that x squared. You can see in the case for limits to infinity, we're not going first by direct substitution. The rule has changed now. So doing that, it means we take each of the terms in the numerator, divide them by x squared. Each of the terms in the denominator, divide by x squared. And we have this now, 3 minus 1 over x plus 4 over x squared, or all over 5 plus 2 over x minus 1 over x squared. Now, remember the rule I said, once you have a constant over x raised to power anything is 0. So all this 1 over x, by the time we plug in our limit, it becomes 1 over infinity. 1 over infinity we are saying is 0. 1 over infinity square is 0. 4 over infinity square 0. 2 over infinity will be 0. 1 over infinity square will be 0, which is the next step. So by direct substitution, I'll plug in infinity and all those terms having x as denominator they will become infinity or infinity square, and they all turn out to be 0. So we're left with 3 over 5, and that's our limit. That is, as x approaches infinity, that function will approach 3 over 5. Now we have another example where the power in the numerator is less than the power in the denominator. Our function is 2x plus 1 over x cubed minus x plus 5. In the denominator, which we are concerned with, the highest power is x cubed. Divide the numerator by x cubed, divide the denominator by x cubed. We have a new function, limit as x tends to infinity, 2 over x squared plus 1 over x cubed over 1 minus 1 over x squared plus 5 over x cubed. And of course, we know that by the time we plug in our limit, 2 over infinity squared becomes 0, 1 over infinity cube becomes 0. In the denominator, we have 1 minus 1 over infinity squared becomes 0. 5 over infinity cube becomes 0. So we'll have 0 over 1, which is 0. 0 is a defined number, like I said earlier on. What we don't want is something over 0, but in this case we have 0 over 1. 0 over 1 is 0, which is defined, and so we're saying this function 2x plus 1 over x cubed minus x plus 5 will approach 0 as x approaches infinity. I have one other example. In this case, the power in the numerator is higher than the power in the denominator. We have x raised to power 4 in the numerator, x squared in the denominator. Let's see how it goes. For the denominator, which is what we are concerned with, highest power is x squared. We'll divide through. Our new function becomes x squared minus 2x over 2 plus 1 over x squared. And if we plug in our limit, infinity square is still infinity. Take note, 2 times infinity is still infinity. At our denominator, we have 2 plus 1 over infinity square is 0. So we have infinity minus infinity over 2, which is infinity over 2. And infinity over 2 is still infinity, right? Infinity times anything is infinity, infinity plus anything is infinity, infinity minus anything is infinity, infinity divided by anything is infinity. What we don't want as results for limits to infinity is infinity over infinity. That's undefined, but infinity divided by a number is still infinity. And so we're saying this function x raised to power 4 minus 2x cubed over 2x squared plus 1 will approach infinity as x approaches infinity. So we're saying a shortcut here that says for any function at all, once the degree in the numerator is higher than the degree in the denominator, then automatically the limit is always infinity. Now there's a concept called continuous functions. We'll just rush through it briefly, and then the next thing you'll be seeing is differential calculus. What is a continuous function? A function f is continuous at a number a if all 3 of the following conditions are met. The first condition is f of a must be defined, and then the second condition is that the limit of f of x as x approaches a must exist, and finally the limit of f of x as x approaches a must be equal to f of a itself. Now this second condition, for this limit to exist, then the limit of f of x as x approaches a from the left and the right must be defined. That's when we can say this limit exists. We'll see all this in an example. If f is continuous at every number in an interval, it is said to be continuous on that interval. Okay, let's see this example. Determine if f of x equals x squared minus 4x plus 7 is continuous at x equals 3. Now, this is just at a point x equals 3. We want to determine if this function is continuous at that point. So just apply this definition step by step, and we'll be able to determine if the function is continuous. So the first step to check if f of a is defined. In this case, of course, our a is 3. So f of 3 means we'll substitute 3 into this function. We'll have 4. Of course, this is a polynomial function, and so it's f of a will always be defined. The next step, we need to check for the existence of the limit f of x as x tends to 3. Alright, because it's a polynomial, it will also exist. So as values of x approach 3 both from left and right, this function will approach 4. And finally, the last condition says that limit from left and right, is it equal to f of a itself? Yes, you can see they are both 4. So this function is continuous at that point, x equals 3. Another example, we have a rational function, and those are where issues arise, because that's where you can have undefined limits. F of x equals x squared minus 4 all over x minus 2. We want to determine if this function is continuous at x equal to 2. So for f of a, you can see substituting a directly into this function is undefined. So we don't need to go further. Once any of the conditions are not met, then the function is not continuous. So this function is not continuous at this point, x equal to 2, right? The solution went further to check for the existence of this limit, and the limit exists, but because f of a is undefined, the entire function x squared minus 4 over x minus 2 is not continuous at x equal to 2. There's a jump discontinuity or a removable discontinuity at the point f of 2. Now, finally, we have a piecewise function. We want to determine its continuity at x equal to 4. Now, there's a constant that is not given in the function. So if you find the value of that constant c, that makes the piecewise function continuous at x equal to 4. Right? So this is how we go about this. For f of x to be continuous at x equals to 4, the limit from the left must equal the limit from the right. That is, the limit as values approach 4 from the left, that's 4 minus, must be equal to the limit as values of x approach 4 from the right, which we define as 4 plus. So evaluate all that on this function. Because the pieces in the function are polynomials, we already know to satisfy f of a. If we plug in 4, it will be defined for both pieces. Now, the main point now is the third condition. We want to use the third condition to know what value c must take so that f of a will be equal to the limit of f of x as x tends to 4. So from the left, we'll evaluate the first function, and from the right, we'll evaluate the second function. So we equate them, the results, and then we'll be able to get a value for c that makes the limit exist from both left and right. So for the first function, the condition is that x is less or equal to 4. Our function is 2x plus c. If we plug in 4 directly, because it's a polynomial, we'll have 8 plus c as our result. 8 plus c is defined as far as c is a constant. And then from the right, our function is x squared minus 3. We plug in 4, 16 minus 3, which is 13. For the second function, the result is clear, but the first function is where we have c, which we need to evaluate. We need the limit from the left to be equal to the limit from the right, and so c here must be 5. For the function to be continuous at x equal to 4, c must be 5. You will notice that once c is 5, if you try f of a, f of a would be 13. That is 2 times 4 plus 5, 13. And then for the second one, 4 squared 16 minus 3 is also 13. And 13 is equal to our limit from the left, which is 13, limit from the right, 13. And so that function is continuous at x equal to 4. So the condition is c must be 5. Thank you. The next class will be discussing differential calculus.